Hi, I'm Joe Rozner. You want to introduce yourself?
And I'm Richard Meester.
We're software engineers at Previty. For the last years and a half or so, we've been working on techniques to integrate tools we've been building into applications. And this is a bunch of our research that we've done to, specifically in .NET and Java, to basically take all the tools we've built and inject them into applications so it reduces the barrier to entry to actually start bringing these tools into applications and adding security layers on top of them. If at any point in time we go over something that you don't understand, just yell or raise your hand and interrupt us, and we'll try to explain it. We're going to do some live demos, and hopefully they work, and go over some code as well. So said, if you can't see anything or you can't understand anything, just stop us. That being said, let's go. I'll wait for everyone to come in really quick. All right, so the problem we're talking about is that we have apps. We have a lot of apps. We've got legacy apps and apps without source code, apps that we can't change, and they have vulnerabilities. We have backlogs of them. We have scanners running. We know about the vulnerabilities we have, but either we can't fix them because it costs too much money to do it, we don't have the time, we don't have the resources, but we know we have them, and we know we have to stop them and remediate them. Attackers know this too. They typically have a lot more resources than the engineers do. They have access to tools and new techniques that engineers have never seen before. They typically have nicer tools than a lot of the engineers do. And they don't have to worry about a lot of the same issues that engineers have to. They don't have deadlines. They don't care about getting new features out. They don't care about the stability across systems or what the customers want. All they care about is finding the bug, getting in, staying undetected, and getting persistence. It makes their job a lot easier, and it makes our job a lot harder. Like I said, they have access to custom tools, cool tools that we probably don't know about. And they'll always be ahead of us. They will always be ahead of the defense's signatures, ahead of the defense, because they're the ones on the bleeding edge. They're the ones figuring out new ways to get in as we stop them. There's a lot of current strategies out there that we're using to stop these types of attacks. There's endpoint protection, there's WAFs, IDS, IPSs, network firewalls, sandboxing, containerization. These are just a few of them. There's many more out there. But they don't really take into account the application itself. And the application itself is where the vulnerability is. That's where the problem arises. Most of these focus on external, looking at the application or at the operating system itself. They focus on isolation so that if an application is compromised, they can minimize the effect of it. It can stop exfiltration of information. It can stop spreading out to other applications and servers. But they don't really take into account where the vulnerabilities are happening. They look at the kernel, they say, hey, notify me if anything is happening here, or block off access to these resources. But that's all that it gives us. So our goal here is that we want to easily remediate known and unknown vulnerabilities. And this is the big thing, is the unknown ones. Because we know we have them, and if we know we have them, we can at least theoretically go in and start fixing them. But the unknown ones are the ones that are really dangerous. These are the ones that we want to stop, get notified that it exists, and then can go in and fix it later. We want to know when it's attempted. We want to get the W's, who, what, where, when, where this is happening in the application, how it's happening. We're not going to attribute probably because it's pretty unrealistic to actually ever do that. But I mean, we can get an idea of where it's coming from and what's going on. We want a minimal impact to performance. One of the things that is really unfortunate is a lot of these tools can really drastically affect that. If your application suddenly can't service requests anymore or gets cut in half in terms of how many it can do, it's no longer a viable solution. So we need a minimal impact. We want no code changes or as minimal as possible. And that's because a lot of the time, getting buy-in from engineers, getting the ability to bring this in, it's a lot of work, and you don't want to have to go there and have to rewrite your whole application just to fix these flaws. And we need to have a low false positive and negative rate. If we have false positives and negatives, we can't run it in production mode. We can't use these tools in ways that are actually meaningful. Sure, they can give us information about when attacks are happening, but if we can't actively prevent it, what's the point? Like, yeah, cool, we know we got owned, but it's already gone. The data's gone. So we're not saying don't fix the root cause. Like, of course you should fix the root cause. Like, you know about it. But we need to have some kind of stopgap in the meantime, because we don't always have the opportunity to do that right now. We don't want to say just put a vendor in front of it. That's also not going to fix the problem. You shouldn't be outsourcing your security to a vendor. Like, you should have the actual problem fixed. And it shouldn't be the final solution that you're going to use. And they're not a replacement for doing things right the first time or after when you actually have a chance to fix it. So don't rely on third parties. Like this should still be something that you're focusing on in your own development. So we're going to talk about the two different types of hooking techniques that we've been using. The first one is middleware, and the second one is using instrumentation APIs to kind of build your own hooks if there are hooks that you want that don't exist yet. So with respect to middleware, these are typically like plugin systems. A lot of the time, your framework will give you these options. They'll provide you hooks saying, hey, there's a database call happening, or hey, there's some data coming in here. I want to have this callback that can go and look at that data and modify it or look at it and do something with it. Typically, there's documentation. Your API will give it to you. We'll go over the servlet implementation and what's the .NET HTTP module as specifics, but virtually any framework out there that you're going to use for any type of application is probably going to have some kind of middleware tier where you can build in a solution. They're typically blocking requests, meaning that when the middleware stack calls your callback, it's going to block that request until you return or yield control, meaning as long as you have control and are executing code, you're going to be there owning that request, and you're not going to let it go through. And this is good and bad, because it can tie up resources and mean if you don't build things right or well, or you don't take into account performance, you might have some serious issues. You might stop the application from processing at all. Overall performance impact is relatively small. Like the actual calls themselves are pretty low. It's basically just a new stack frame being pushed on and then doing whatever actual processing you're doing. And with respect to HTTP, which is what our demos are going to be based on, typically you'll deal with like requests and response, and these are the two pieces of data that you'll have access to in this middleware chain. And the request is basically just the HTTP request coming in, all packaged up into a nice object, and the request is the response is the one that comes out that has the headers and the body and everything else in there. The specific use cases we've targeted and built tools for are adding security headers, so like HSTS, CSP, XSS protection, etc. These are all things that you can easily build middleware that can basically inject these headers or verify that they're there or modify headers that are there to add these in if you wanted to. And it's pretty low-hanging fruit in order to actually build these. Validating the correctness of headers. These are like MIME types, content length, anything where these headers, the application is going to do something based on that data. This is a good place and an easy target to be able to validate that and stop the request if the MIME type isn't correct or if some part of the header isn't correct. You can sanitize parameters, so the body of a put or a post or a patch request, query parameters in a GET request. You can force cookie headers, so if you wanted to add on like the secure bit or the HTTP only bit, that's something you could rewrite in real time as the request is going through. And then inserting and validating CSRF tokens. And this is also a big one. Just being able to, like on the fly without having to know anything about the application, even if your framework doesn't support it, you can generate a token and then on the way back, you can validate that that token is in fact valid. And it's a relatively easy thing to do. Specifically with the Java side, this is a diagram from Oracle describing how their middleware tier works for their servlets. I wish I had a laser pointer, but you can see the servlet container, which is basically where when a request comes in, everything comes to that point, and that's when the application starts taking over. The application lives in the container, and it's going to get passed off to that. So you see, do I have a mouse? I don't have a mouse. So the servlet container and the servlet are right there. And you see like comes into the container, the request gets sent off to the servlet, and then the servlet does its magic, whatever it has to do, packages up a response and sends it back. So in Java, they have this whole filter chain here. And as you're setting it up, you can go in and say, I want to build these filters and I want to attach them. And they execute in the order that they're inserted into the chain. And they basically just pass off control to each other until they hit the actual servlet. So as you go all the way down from the container to the servlet, you're going to go through every single one of those. And they all have the opportunity to make changes, to inspect it, to stop the request. And then after it hits the servlet's going to process it, do whatever it has to do, and it's going to go all the way back through in reverse order. So the last one before it got handed off to the servlet, that one starts and it goes all the way back until it reaches the container, and the container returns the response. Building these is really simple. There's an interface that Oracle defines, and as long as you adhere to this, you can basically build a filter. There's 3 methods you have to implement. The do filter is the important one. This is what gets called by the filter in the chain. So like when you pass off control, you just have to call do filter of the next one. Init is called when the container sets up the actual application, and destroy is called when it finishes. And this can be used for setting up state or killing state or saving state. And passing between. And these all have to be thread safe, so you got to make sure you don't do anything like weird with that, and you can definitely cause problems if you don't. There's another issue that we came up with when we were building a lot of these, and that's wrapping. So there's a lot of things in the servlet spec where they're destructive. So when you get in a request object, that request object is going to have a body and a parameter map and a whole bunch of data in it. And say you want to read that parameter map. In order to do that, it has to, on the other side, go and read in the entire body of the request and pull it off the wire, and it can't rewind that. So once it's been read in, anything else down the line that wants to read in that body, it's going to fail. So one of the techniques that you can use is wrapping. The requests and the responses are typically designed as interfaces, so you can basically build your own object that implements the request and the response objects. And basically what you do is you delegate. So you take the original response and the request that got passed to you, you put it inside your wrapper, and any of the requests that come to you, you delegate to the inside one. So you have to, say someone calls read on the body. You then read in that thing off the wire, and you put it into a buffer somewhere, and anything else that ever calls it on your wrapper can then still make use of that and actually get the data out of it. So it's really important that you play nice in the filter chain. You don't want to like have any expectations that, you know, I made this call so no one else down the chain can. And this can cause problems if you start inserting filters in the wrong order. If you know, you just need to be a good citizen in the middleware stack. Like you don't want to cause problems for anyone else, because you're going to take apps down and it's going to be bad for everyone. There's a whole bunch of documentation online in the Java docs for this about what can and can't be done, and there's a lot of example code out there about building like really, really robust wrappers. I will try to get some links up after when I post the slides. Wanna?
All right, so I'll be popping in and out, talking about how we do it on the .NET side. So with it was the introduction of IIS 7, I believe, they had allowed you to run your application pools in a new mode it's called a new pipeline mode. It's called an integrated mode. And basically, what that means is now you can use managed filters in the request processing pipeline. Whereas before in IIS 6 or if you're using classic pipeline modes, you had to write ASAPI filters. So that was all basically like C++ code to do request processing. But so what this allows you to do now is with HTTP modules, you can plug in callbacks at different points of the request processing sort of chain. So you can do it at the beginning when the request first gets in. You can kind of do your stuff on it then, or when the response is headed out at the sort of the end of the pipeline, you can plug in a callback there, and it allows you to inspect and modify requests during the processing. So the way it works now is each request and response that comes in has a filter field where you can plug in a filter, and when some part of the pipeline says, hey, let's read the form data for this HTTP request, what happens is the body of the request will get processed, it'll get run through whatever filters are hooked up, and then the results are sent out to whoever called like the read function. So that's basically the most convenient place to if you want to do inspection of body content. That's kind of where we plugged in, and it's a convenient means for doing that, because now everybody who does like read the form data will be forced to go through your filter. And so the next slide, this is just kind of like a little demo, or not demo, it's just kind of hello world for HTTP modules. And as you can see, so we have the third function in that list, begin request handler. This gets hooked up in the pipeline at begin request. So when the request first gets sent to the server, our function gets fired, and all we're doing is ending the request and sending back hello world. So regardless of whatever's running on that server, this is now what they get back. And so it's kind of a basic example of how it works. You want to then talk about instrument?
Yeah. So this has all been like, yes.
Yes, you can. I mean, it's yeah. Okay. So yeah, you do have access to all of the headers. The filter only gets applied when you are doing anything that processes like the body content, but the headers and all of the cookies and all of that stuff, those are all separate collections that you can modify, and then as the request gets shoved down the pipeline, those modifications stay. There are some gotchas though. So in IIS 7, you can configure your site to have different application pools, right? And each application pool can be running a different .NET framework. So you can have a 2.0 application pool and a 4.0 application pool. And there's some gotchas in there because of the way that requests are handled in 2.0 versus 4.0. So in 4.0, you can read the body in as many different ways, as many times as you want. So you can read the form data as part of the form collection, or you can do .read binary and read the request as a binary blob. And in .NET 4, that works just fine. But if you do it in 2.0, if you read forms and then you try to read binary, it'll flip out and it'll throw an exception. So there are some gotchas in there. So when you are handling requests, you kind of have to, I guess, be cognizant of sort of what framework you're running in, and you have to kind of take steps to sort of work around that.
So we've been talking about middleware, and middleware is great when you have access to it, but a lot of the time you're limited in what you can do. The framework will decide what they want to give you access to, and you're kind of stuck with it. So one of the things that we really wanted to do in Java was have a cross framework way to hook every single query that ever went out, no matter what framework or driver you're using. And so we had to build our own hooks. And we'll talk a little bit about how we did that. Typically, any managed language that runs on a VM or has some kind of, any modern language, has some type of instrumentation layer. There's usually an API that's made available to you that lets you do all kinds of nice things like profiling and setting up hooks beforehand. You can modify code as it's being read into the VM. You can set breakpoints and all kinds of really, really awesome functionality that you probably never knew you could do or knew to ask how to do it. And you'll want to look up like instrumentation or profiling APIs for the language or the platform, and that will typically give you a good head start into like where you need to go find more information for it. And so like I said, our use case was SQL. We wanted to hook every single query going out. But there's a lot of other really useful things. If you want to look at network requests, opening a socket somewhere, looking at where it's opening it to, what port, the type of socket, file access if you're opening a file, what file name, how it's being accessed, exec calls, the actual string that's being sent off to execute, database access, like I already said, changing permissions, what the current permission is, what it's going to, content validation. So does this content, you can validate the content without having to write it into your application in the first place. So like if you know, this should always be a credit card number, but you can't go and fix that, line of code to verify that there, you can say, hey, I want to hook this before it ever gets accessed, and I want to verify that this actually does match the type of data that I want it to be. So finding your hooks is like the real important part, and this is like where you want to hook. So you want to identify execution choke points, and by execution choke points, I mean you want to find the low-level APIs that everything's going to filter down through. Typically, these will take the form of syscalls or really low-level library functions, but you don't want the hook like see every single printf function, because that's going to be really, really hard, and you're going to have to hit every single one of them and make sure you go through every single one of them. So you want to hook like the one that all of them go to, or the write system call where all of them eventually write to. Reflection is going to be your friend. Does anyone here not know what reflection is? Cool. All right. So as you're reading data in and you're looking at the types, like use reflection, figure out like what it is. You can look at names of classes, names of methods, types in classes. You can look at namespaces of where things are placed. You can look and see if something is an implementer of an interface or if it's subclasses from something. And these are all really useful things that we've used in our work in order to determine if it was the thing that we wanted and then the correct method on that thing that we wanted. You should change as little as possible. Aim to be like really precise and do as little as possible to actually change it. It will increase stability, and you're not going to worry about like just totally trashing the code. You should favor trampoline use, so replacing functions or just literally replacing the first instruction and jumping out to your code to handle it. Don't modify like whole function bodies if you can avoid it. It can be a bad time, especially if like you don't recalculate sizes and jump points correctly. Bad things will happen. There's a couple different ways to build your hooks. And the two main ones are caller versus callee. And what I mean by this is that in a function, say you want to hook the printf function, and you can either go to everywhere in the application where printf is called, and that's the caller method. You are hooking it in the caller and you're replacing it. Or you can go to the callee, which is the printf function itself, and replace just that one point with a new version of it. And your new version will then call the original one or do whatever it has to do and add whatever checks to it. Callee is typically a lot easier because it reduces the surface area you have to go through. It makes it a lot easier to target what you want to, and you don't have to make as much modification to the entire application. and it's also just a lot easier and faster to do. And then, like I said, there's also method replacement versus modification. You can modify the method, or you can replace the entire thing with a new pointer. So wherever the pointer is that that method used to refer to, you just replace it with your thing, and then your thing can call the original one. And it's like you just replaced the entire method, but never modified the body of it itself. Efficiency. Callbacks are typically blocking, like I said. You should keep this in mind. Like you will be blocking the request when this is happening, because it will stop until you yield control. You need to understand the effects of garbage collection that your code is going to have. You're probably going to be allocating some objects. You're probably going to be doing some work. And this can slow it down. If you're generating a ton of garbage, you might get GC pauses, or you might get the entire application just heading those big weights to clean it up. So be careful with what you do. You'll probably have a slightly longer startup time. A lot of these systems, the way they work is that it does a pass through in the very beginning as files are being loaded in, or as the application is loading up. And so doing all this extra work to set up your hooks, it might increase the startup time, but once it's running, the actual performance impact is pretty negligible, unless enabling the APIs itself turns on other functionality that slows it down. So as long as your code isn't slow, you're probably not going to see a huge slowdown. We run this code in production, and we've had no issues in terms of performance. The only performance issues we've had is in our code itself, not in hooks. So you might produce more output or make the VM do extra work. Like if you're printing out a whole bunch of just standard outs and it's not being redirected, it's a really expensive operation, because it's a blocking operation that takes like a real resource. So you should be cognizant of what you're doing with the computer's resources while you're here. Doing it in Java, they provide this really cool thing called an agent. And agents are a way to basically, it provides instrumentation access so that you can make some changes to the VM and do some work before the application starts getting loaded. They're typically deployed as a shaded jar, which means that all the dependencies are packaged into the actual jar, so it's not going to pull from your class paths. This is important because if you don't have all the dependencies of this thing that you've built in your class path, and you don't bring them in manually when you're doing this, which is a pain in the ass to do, it's going to just completely fail, and you're going to take down the VM before it even starts the application. So use the shade plugin with Maven or whatever your build tool is, and package it all nicely. It makes it bigger, but it's really, really nice, and just makes it a lot easier to deal with. And the way that it basically works is you set up this class transformer, and I'll go over that in a minute, where every single class file that comes into the VM basically passes through you. And you have the byte stream, and you can go through and you can disassemble it, and you can figure out what it's doing, and you can look for things you care about, and then you can modify it. And then you can return that byte stream, and the JVM will then load that in and use that rather than the original one. You make no changes on disk, it's only in memory, and it happens every time at startup, rather than having to do a whole recompilation step. Project-wise, check out Java Assist. This is what we use. It's really nice, and as far as I know, there's nothing else out there in the Java world that's as stable or well used. Under the hood, I think a lot of the AOP stuff uses this, or some of the things that this uses, and I'll go over that a little bit later as well. This is more or less what it looks like. You basically have this pre-main method that you define, and a method called transform. When you do the pre-main, you basically can say, hey, instrumentation layer thing, just like add in this transformer for me. And it will do that. And then every single time a class is loaded into the VM, it will call that transform method, and it returns a byte array back with the actual byte code that it's going to then JIT and turn into code, or into machine code. So let me do a quick demo showing how some of this works. Let me switch over to the mirrored. I always forget what that is. Cool. So far, so good. So this is my, that's definitely not readable. How do I, is there a way to change this font size on this?
In IntelliJ?
Yeah.
You're talking to the Windows guy, dude.
Does anyone know how to do this? I think this,
I think you can zoom in with command and then just do it. What did I do? No, so that's,
Apple Zoom?
yeah.
It doesn't work anymore.
I guess we'll just have to make do.
Can everyone read that? No? All right. Let me see if I can. There's got to be like a.
View? Go to view.
Where's view? There's view. Presentation mode?
Boom.
Cool. All right. Yeah, IntelliJ is not always terrible. So this is like a really, really simple application. All it does is take the first parameter from the command line and prints it out. How do I exit presentation mode now? So we can run it.
Oh, jeez.
I can definitely make this bigger. I know how to do that. All right. Is that readable? Bigger? All right. So it runs and it prints out the thing and it's all cool. And let's go look at the, how do I switch tabs now? Exit presentation. Oh, where did it go? That really didn't help me. All right. So this is more or less the implementation of the agent that I built. This is the transform method. The pre-main is like really, really simple. All it does is wire it up. And basically all it does is it inserts the current package into the class pool so it can access the actual classes that we're defining in here. It then creates a new byte stream of the actual class file, and it checks, it does some like magic stuff with Java Assist, and it checks to see if the class is frozen. If it's frozen, we're not gonna be able to transform it. But there's other ways you can deal with that. We want to make sure that we don't hook ourselves. That would be bad. We've done that in the past, and bad things happen. You end up like replacing methods that you don't want to, and then everything kind of breaks and falls apart. Then we go through and we look at all the declared methods on the class, and we determine whether or not this is, in fact, the method that we want to look for. We want to look for print line, and so we go through and we check if the class is the Java IO print stream, which is where print line is defined, and then we do this really cool thing called method replace, and this is some really nice syntaxy stuff that Java Assist gives you to basically pass in some information, and then we return out the bytecode. The other side is we declare this shim, which is our implementation of printline. And this is just basically our implementation. All we're going to do is we're going to check if a script tag is there. If it is, we're going to throw an exception to stop the thing from processing. And if it's not, we're going to go through and using some reflection magic, we're going to call the original method. So I'm going to exit presentation mode. And we're going to go back here. I think I still have this. Yeah. So we see this execute still, and this is all fine. Then we go in and we can add a script tag, and it throws an exception because we caught it and we intercepted that call and we stopped it from executing. Thank you. Cool.
All right, so the .NET framework, right? They provide this kind of neat thing. It's called the profiling API, and basically what it allows you to do is write. Well, so basically what it allows you to do is hook into the .NET framework at runtime. So when you double-click that application on your desktop, right, the .NET runtime gets loaded, and then it starts loading in all the system libraries, and it starts, jitting stuff. So what the profiling API allows you to do is plug in your own DLL that has callbacks for when different events occur during the during execution of the runtime. So one of the things that you can do is you can hook into the JIT compilation events. So when JIT compilation starts, you can hook into that, and you can then take the IL code that's going to be compiled into assembly, and you can modify it there. So that's kind of what we do. I guess something else is actually, we should probably just skip to the demo because we're running out of time here. All right, so let's just do this. So what I'm going to do is, first of all, I'm going to show you. So I have a test program.
Change the mirror.
Oh yeah, okay, that would probably help.
Right there.
This guy.
Yeah, and then just hit mirror displays.
All right. Now everybody can see what I'm seeing. Okay. Can I? Oh no! Don't do that. All right. Well, does this have a presentation mode? I guess so. It's got a full screen though. Okay. Maybe. That does not help me at all. All right. Oh yeah, this guy. Whoa. All right. I guess a little bit better. All right, so I have this test program, right? It just contains a loop that goes on forever, and it calls this one function and then sleeps for a second. And in one, it's just printing true or false based on the value of this flag, but because the flag is set to false, it will just always print false. Now, I'm going to pull up, I guess my favorite tool is the IL disassembler. So you can look, this is the one function, and this is the IL code that it gets transformed in, or I guess the compiler turns it into, right? And so these are the instruction bytes and the associated actual IL instruction. So now so that's kind of, I guess, those instructions. So now we have the actual profiling API code, and this is what gets loaded. This is what gets loaded in at runtime by the .NET framework. And so you have this interface that you have to kind of build against, and it has all of these callbacks. Oh, geez, it's super tiny. These are all of the kind of possible callbacks that you can hook into. The one that we're interested in is JIT compilation started. But I mean, there's a ton of stuff here that you can hook into, and it gives you a lot of power to basically modify a assembly's metadata and its IL code at runtime. So you can do whatever you want. One of the things is, you can insert your own, you can build your own classes dynamically, and then have pre-existing functions in the system to call into your dynamically created classes. There's a lot of power here, but there's a lot of power, but the documentation is really bad. So you just kind of have to experiment and try to figure it out on your own. So we have this kind of important function here. JIT compilation started. So when a function gets called the first time, the way .NET works is that it'll take the IL, it'll compile it, and then it'll save it as an assembly blob in memory, and then all future executions of that function will just go to that blob in memory. So what we can do is when a function gets started, there's a bunch of stuff here, but basically we're pulling the function metadata. All of this stuff is basically getting the function metadata from the assembly and getting the assembly name and things like that. And this is the important guy right here. So we're getting the function, the IL code body. When you get the body, so the thing is right, the body is stored in read-only memory. but they give you the ability to allocate new IL, a new IL like memory blob. So you can basically allocate a new block for your modified IL, copy the old stuff in, modify it, and then switch the pointer out. So that's kind of what we're doing in here. So we get the IL function body, we allocate a new space for our modified version, we copy the old code over, and then all I'm doing right here is I'm changing one instruction, which would be, I'm changing this instruction from 16 to 17. What that basically is doing is just reassigning, it's forcing this to true rather than false at kind of execution time. So, and then we set the new function body back. So I'm going to run this, and it compiled earlier, so we shouldn't have any problems. All right, so the unhooked one is just false, 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 blah, blah, blah. And then the hooked one, right, so it's now true. It's now printing true. So the first kind of line up, oh, that is way small too. Well, the first line up here is, yeah, probably. Whoa. Yeah, there we go. Boom. All right, so yeah, the first line is the original IL code, and the second line is going to be the modified IL code. All right, stop. So yeah, it's kind of basic, but this kind of shows you, I guess, the power that the API, the profiling API gives you, because like their intent was just allow people to, I guess, instrument their own code, kind of using their own instrumentation, but I mean, you can do whatever you want with it. That's what it comes down to. All right, so do you want to switch this over, I guess? Why is that like that? All right, there it is. Cool.
Keynote. I want to talk about AOP, but we're going to wrap up right now because we're basically out of time. AOP is cool. It's basically an abstraction of a lot of these ideas, but it's got a lot of just not great things about it. It's usually not as powerful. You typically can't do it at runtime. You have to recompile unless you have a runtime code weaver, and a lot of these don't allow you to do it without doing it at compile time if you want to change system actual built-in stuff. There's relatively poor documentation depending on what it is, but we'll put these slides up and we'll go over it elsewhere. In conclusion, focus on the application itself, utilize built-in middleware hooks and instrumentation to build your own, find choke points to minimize impact on application, change as little as possible, and test everything you're playing with Fire. And let's do questions.
So thank you. I think you could give them a warm round of applause.